will share the screen first. Let me share my screen. Okay, can you see my screen now?
Yes.
Okay, great. Okay, good afternoon, and I'm very happy to present this paper, Learning Transferable Visual Models from Natural Language Supervision. And from the beginning, I actually was fooled by this title, since this title is let me feel like this is more like an NLP paper. And after I read this, I found this one is actually not an NLP paper, it's more about image processing and CV. So I'm quite, I'm just quite nervous about this one because I'm not really an expert of the image processing. And this presentation is most based on my understanding of this paper. So there may be some mistakes, and if I make mistakes, please just cut in and interrupt me to correct these ideas, and we can start. And first one is about backgrounds. The background is about this paper is more about combining techniques of NLP and CV and into one application. So maybe I need to introduce the background from both NLP and CV. So let's start from a very important concept, pretraining. I will use this in use pretraining in NLP to explain this. And if we mention pretraining, most of us will, if you Google pretraining on the web page, and you will mostly find two words. One word is transformers, and the other word is BERT. And these are really hot models. And at the first time I searched this website, I just get confused. So what's the relationship between BERT and transformers? I know BERT, I know transformers, but I don't know what's the relationship of them. So it made me quite confusing, and I learned both models for maybe a month to finally figure out what's the relationship between BERT and transformers. And I don't have to introduce this today because this will make this presentation so long and so boring. So if you really want to know the relationship between BERT and transformers, you can learn it after the course. And I will just introduce pretraining from our own experience. Since we are most of us are students in computer science, and we need to I just want you to recall when you first learn a programming language and how long that costs you. For me, my first language is C++, and it cost me maybe a month to fully master the whole language. And this language makes me fully understand the idea of the coding language. And in the following time in my college, I learned Java and R and Python. And I found that the second time I learn a new programming language will cost me less time. In this picture, the first 1 month I learned like Python, and when I want to learn Java, I only need 1 day to get all the Java idea and know how to build a class and how to write a new function. And when the situation comes to R, I found I just need to cost my 1 afternoon to learn this, because R has really similar properties as Python. So this won't cost me too much time. So this is a very great pre-training process, because at the first, I don't know, I know nothing about a programming language. So I need to learn a lot of things, like how to define a variable, how to write a compiler cracked codes, and how to build a fully functional function. And so this cost me really long time to understand the idea of how to write a code. So I need 1 month to learn this, and also with a lot of knowledges. After I get these knowledges, I don't have to learn these knowledges again because most of programming language are same. So I only need 1 day or 1 afternoon to finish how the some different property of this one language. For Java, I need to get some object-oriented ideas, and for R, I just need to know how to make matrix multiplication. So I will define the first stage at pre-training. We need to get a lot of knowledge and need to go through many data to get the information we need. And once we get those information, we can quickly adapt to some subfields, like I need to learn Java and in R. And those knowledges really don't need us to cost those many knowledges, and we don't have to search those many knowledges. So we can learn this very quickly. So this is most same as the like the model. So the model will just the pre-training of model is to use many really large data to train a model, and fine-tuning is about when we want to build some model for some specific task. We just need some much less data than the pre-training to let the model quickly learn the whole process. And the second concept I want to introduce is about fine-tuning, few shots fine-tuning, because in our real life, something is very some resources is very limited, like cancer images. They are really limited. Cancer images is quite less than the images of horse or some animals. So we want to use those few shots. We just want to use very limited resources, maybe just 1 or 2 images to build a model, to let the model know, oh, this is this thing. And I want you to experience this. So I found the image. Maybe most of you don't recognize this. This is a unit in StarCraft 2, and it was called the Overlord. And maybe you have not exposed to this creature. And this is the only image I want to train you. So you can just, based on your pre-trained knowledge of animals, insects, and to have a first step of recognition of this one. So after this one images, I will show you the 4 test data. And you can see the first one is an overlord, and the second one is an overlord, and the third one is also an overlord. But the fourth one is somehow strange, and they seems like overlord, but they are not. It is not. It is called seer lord. It has some difference between the images of the overlord. So I just use one images to train you, so that you can judge those if these pictures are overlords based on just one picture. This is called one-shot training. So humans are really good at the one-shot training or few shots training, but models is quite hard to get this. And there is a very classic pre-training and fine-tuning pipeline I want to introduce you. And this is the classic algorithm in NLP. It's called WorldtoWack. The full name is WorldtoVector. Because before maybe 10 years ago, most NLP researchers don't know how to represent a word in a dictionary. In our case, you can see we can have a really small dictionary. It's just have 5 words. So the old-fashioned way to represent one word is just to indicate the position of this word in the dictionary. Like apple is the first position, so the first index is 1, and the other are zeros. So using this is quite disobey the property of a language, because our language has some context. We need to use this context to infer the meaning of this word or the whole sentence. And just using the position of in the dictionary is not enough for those contexts. And the one most property of language is synonyms. That are 2 words are really similar, has similar meanings. And as we can see, if we want to get some similarity of those two words, like cat and dog, we can use multiplication of those vectors, and you will find their similarity is 0. And if you want to get the similarity between cat and bad, you also get a 0. So there's no difference between the similarity of cat and dog and cat and bad. So this is very bad representation of words. And after some day, this algorithm just magically appears. And I don't want to get into too much detail of this algorithm. I just want to give you some basic knowledge of this one. So this one is just about there's a black box on the screen, and you can see this is a magical box. And we just need to input some words and sentences and through this magical box. And the output will be some vectors. And those vectors, maybe you cannot see the meaning of each vector directly. But if we calculate the similarity between those words like cat and dog, we can find the similarity is 1.12. And the similarity of cat and bad is just 0.1. So this representation can be a very good one to represent some property of the language. So we can see those vectors like some features of each word. So like the apple have one vector. This vector can represent some meanings of apple. So after we get those features, we can use these features into other task models. Like we want to do some classification. So we just need to input those features into the other model and to get the final result. And this one is using these word embeddings will have better performance than those one-hot vectors, because it has more meanings of words and it can represent something. And this is some pre-training and fine-tuning or using pre-training features pipeline. Yeah, this is some backgrounds about NLP. And the second background I want to introduce you is about image classification. And image classification, this is a very abstract and class pipeline. And you just need to input your image into something called image encoder to get the feature of each image. The feature I set here is just a one vector to represent those images. Like I will show you, because like this dog images, we can represent it like 0.1, 0.3, 0.4 maybe. And this one into this one, maybe 0.2, 0.5, 0.0, just 0. So we can represent this into some vectors. This is what image encoder do. And we can feed these features into some other networks and get the final prediction. This prediction just means this first box is the probability of this image is a dog. And the second one is the probability of this image is a bird. And the third one is this is the image of the squirrel. So as we can see, if a fully trained this network can predict this very good, since we can see the dog image, it has a very large probability, and those two are really small. So this is a classic image classification problem. But what's the problem is, what do you feel something wrong? Because these classes we have to predefine. We just need to tell the model the images are just from those three classes: dogs, birds, and squirrels. And if I really want this model to predict image of horse, it will be very strange. So the encoder will think, okay, this is a horse, and this one is quite yellow, and this horse has 4 legs, and this image is quite similar to this dog. So it will finally output the probability of dog is really high, and the probability of bird and squirrel is is low, but this is not what we want, because we want the model to predict this is a horse, not a dog. So in the real life, if we have a lot of data, because horse is really common in our life, we can have many horse images. We can use many horse images, and we also have to add a new class called horse, and use those images to retrain the model, and the model will finally give you a really good prediction of the image. And this comes to a really, really tricky problem. Like in the real life, if someday some of your friends took just one picture of Overlord, and the Overlord just has one picture, and you cannot find some really large data set to train this model, and you can add a new class here, but you don't have really many images to let the model know this is an Overlord. So this is some problem of this paper want to mediate. It's just about if we find some new creatures or new classes, we don't have to retrain the model or add some more classes, and it can adapt to this model and adapt to this creature and give some predictions. Okay, let's start from the real one. It's about the method. And I just need to highlight the most contribution of the authors. And the first one is this model doesn't need human manually build one-hot labels, because in the case here, we need to for each image we need to get its labels. Like for dogs, it has to be 1, 0, 0, and this one needs to be 0, 1, 0. Yeah, this is a quite annoying procedure, and no one wants to do this, because our creativity just to invent some new models to change the world, and we don't want to build some data set like just type the keyboard like 010. It's quite boring. So this method don't need human to manually build one-hot labels, and this model combines the strengths of NLP and CV, so that each representation of the image can contain some linguistic context, so that make the transfer to other domains more easily. These are maybe I think this is the most contribution of those authors. And I don't want to start from introducing the model architecture here. I just want to make some experiments of human, because humans are really good learners. So I can train you, and you will understand the whole training method. And let's imagine we have just four images, and this is quite enough for human. And each images are labeled by natural language, because the first image will have, this is a dog, this is not a bird, this is not a squirrel, this is not a horse. And this quite robotic labels just simulates how the model learns. We don't have to learn this. And we don't have to learn this. So that I just simulate how the model learns. So you will have maybe 30 seconds to fully train on those four images. And I will wait for maybe 30 seconds. And you can look at those images and see that because I took those images. Oh, Grayson, I will introduce the details maybe in the following paper. So yeah, the model just contains some transformers or some REST nets for the image encoders. Okay, hope you are fully trained on this one, on these four images. So let me test you. This is just one case testing. I hope you will do this right. And the testing is just more about more about like the multiple choice questions. So the testing will just give you an image and give you 4 sentences, and you need to choose the right one. And for this one, obviously, this is a horse, and this one is this is just similar to how the model are trained. And I will show you the training process of the whole model. And the training process is just like what we did before. The first one is, let's start from the text encoder. The text encoder will receive some text, and this text is just like this. This is a horse, this is a bird, this is a dog, this is a squirrel, like 4 sentences. And the image encoder will give the 4 images of those 4 sentences. And the text will come into the text encoder and form 4 vectors, like here. The 4 vectors is here. And each vector represents 1 sentence. Like the T1 just represents this is a horse, and T2 is this is a bird, and this is T1, T2, T3, and T4. And for the image encoder part, each picture will also go through the image encoder and become a 1 vector. And this 1 vector, the I1 will just represent the image of horse. And for the prediction, it will just use vector multiplication to get a cosine similarity score to indicate how much to pair those image vectors to the text vectors. What I mean is this one is the horse image, and this one is the text of this is horse. And they have to have a really high probability, because this text is just a description of this image. So this one needs to be maybe high probability 0.5. And the second one is just about this is a bird, and the image is also the same horse image, and they need to be very the probability needs to be very small, maybe 0.01, and the other one needs to be very small. So the labels I just list here it's more like some one-hot vectors. The first, for the horse image, this is horse is labeled as 1, and the other texts are labeled as zeros. So this is almost the full training method, and it's quite simple and quite direct. So I don't need to explain this more. And for the testing, it's more like some multiple choice problems. Like we have 4 sentences because our data set just have 4 classes. So I have 4 sentences here, and I need them all go through the text encoder and form 4 vectors. And those 4 vectors are, each vector represent 1 text. And I need to use this new horse image to get through the image encoder and get one vector. And we just need to multiply L1, T1, L1, I1, T2, I1, T3, and I1, T4 to get 4 scores. And these 4 scores can represent the probability of the pairness of the image and the text. So in this case, this image is obviously a horse. So the first one should be high probability, and those 3 are very low probability. And this is the basic training and testing procedure. And for some, I will introduce some details. For the text encoders, Grayson just asked, he saw something like transformers and ResNets. I will explain this here. So this is a very abstract pipeline here, because this pipeline is just a text encoder, image encoder, and this is very abstract. And the authors choose different encoders, but for text encoders, this is just a transformer. and this is the only choice of the text encoder. And for the image encoder, this encoder can be ResNet and can be visual transformer. So I don't know if this can explain your question. So it's more like the author trained many models. One model is use transformer as text encoder and ResNet as image encoder. The other model use transformer as text encoder and visual transformer as the image encoder. So the authors trained many models, so they can test the performance of the whole pipeline. Yeah, that's what I list here. They chose transformers as text encoders and ResNet as image encoders, as well as vision transformers. Okay, the authors also mentioned some tricks while training this model. Like I said, the words, one word can have different meanings. Like if we mention apple, maybe apple is a fruit we eat every day, and maybe Apple is a company to produce phones, iPads. And if we just use Apple as the one word, Apple as the label of one image, and the performance may be dropped because the company can be Apple and the fruit can be apple. So the model can be confused by those two concepts. So they also use one trick. It's called prompt engineering to make clear of the apple. Like the fruit apple, they will add a sentence like a type of fruits, so make the model know, oh, this is the fruit. And for the company, they will add something like a company to identify the image, so that the image can learn the context of the whole sentence and match the image to those text. And this is tricks they used in the training method. And they also introduced a lot of those prompt engineering, like a photo of something or a satellite like this. And I will just show you the idea of why they are using this. And for the experiment, they build a really huge data set. They use 400 million text and image pairs. This is a really big data set. And the training will be so computation heavy. So for the 5 ResNets, the largest ResNet will cost 18 days on almost 600 V100 GPU, and the vision transformer will cost 12 days on 2256 V100 GPU. So they really need a lot of computation power and to make this model to get really good performance. And I don't think we can reconstruct this experiment because we don't have those many GPUs. And I just show this. And as come to the result, the author just in the paper, this paper is really long, and the author used maybe 10 pages or 15 pages to introduce their experiments and show the results and get some logic of why they need those experiments. So in this part, I will show you some key point of the experiment, and I will explain why authors want to do the experiment like this. And the first experiment is really simple. It's just the authors just want to test the clip model use zero-shot transfer to the other data set, because the author used 400 million data, and for the test, they also use some data was not in the training set. So so the author argues that if the clip you can transfer to those images it haven't seen and have good performance, so that the robustness is good and it can show their work is efficient. So for the first three data set, it just shows some numbers. Is in a Yahoo data set, it just have 98.4 performance, and for those two, 76, 58. And if we just look into those numbers, we can feel nothing, right? Because the data is just some numbers. We cannot feel if this method is good and if this method is bad. And you will also notice in the original paper there will be another row to show another model's performance. The reason why I didn't put here because the other model trained on a significantly small data set and has very bad performance on these three data sets. And the authors also admit this is not to beat those models because the data set cannot match, the size of data set cannot match. So I just put this one model to show some performance of this model. And the following experiments are more important. Like the authors use the clip zero shot to versus some fully supervised method. Like the clip didn't see those data, and on some of data set, the clip can outperform those supervised models because those supervised models are trained on the training set of this data. They are supposed to be very good on one specific data, and the clip just trained on some very general data set. Although those data set is really big, but the data set is quite general, so it cannot catch the characteristic of a specific data set. So if the clip zero shot can outperform some supervised models, it can indicate some this model can be used in many areas and can be generalized to many different domains. And this is the logic of the author to perform this to some supervised models. And we can find that I suppose there are 27 data set, and the clip zero shot just outperform on the more than half of the data set. And the one it outperforms to 28.9%. So they also want to use this experiment to show their model can transfer to other different domains. But also, they also reported some weakness of this data, of this model. Like for the this one, Minis data set. Minis data set is just about recognize some handcrafted numbers, like I write one and into the model will just output one. So in those data sets, it needs a model to infer more knowledges, and the clip on those data sets is not as good as on some objective data set like cars. They just need to locate the car or just say if this image have or don't have a car. So this is the zero shot vs supervised models experiment. Okay, I will also show some. The authors also show some few shots experiments to indicate the learning probability of the clip. And this experiment also wants to show the clip can adapt to some new domains. These domains can have very limited resources, like the overlord case we introduced before. because it just has one image, and it needs to fully use this one image to recognize all the overlords. And how they performed this experiment is just use the model clip, the original clip, and add a linear layer, and get the prediction. Yeah, this is the procedure of using the few shots. They build this model and train on few shot data, like 1 data and 2 data, 4 data, 8 data. This is how they perform this experiment. And this experiment can, from this figure, we can say that the linear probe clip, if just this model, can outperform many old models like BITM and SIM classifier and ResNet 15 on some on the few shot cases, because at the start point, the model achieved very convincing performance on just 0 shot, and you can see the performance will increase, and with the increase of the data, like from 4 to 8, the performance will from 18 to 80 to 85. And the other models will just cannot learn that well on those few data. So this can show that this clip model can have really adaptability to the very limited resources domains. And this is why the author made this experiment. And the other experiment author made is about representation. Yeah, I saw a question. Their shot is greater than 1 shot. Yeah, from the report of author, the 0 shot performance is better than 1 shot. And this may be because the 1 shot, it's just maybe 4 shot can just match the performance of 0 shot. Because if we have 2 less data, this data can be some noise or some noise for the model. So the model may not learn the yeah, you can unmute you. But I will continue. So few data can be some noise to the model. Like if the model learns some generalized features of all the 400 million data sets, and if you give it some very few images, so it cannot learn the feature of the whole image. Maybe they will just focus on some not necessary features. Like if I want clip to identify the banana and plane, and the model maybe just will focus on if this image is yellow, and if I give it a yellow plane, it will maybe it will just regard this yellow plane as banana. So this can be some noise, and with the images increase, with the data increase, and the model can find the real feature that we wanted to learn gradually, so it can increase its performance.
Thanks, got it.
Okay, let's go on the representation experiment. The representation experiment is more similar at the case of the word embedding I just introduced before. Like the authors just use the image encoder's output as the feature of the image, like the graph showed here. I just noticed this image encoder. This image encoder is freeze, so it will not influenced by the training procedure of the following task. So each image just will go through this freeze encoder, get a feature, and we can use this feature to other models and to get some predictions. In experiments, they just use one linear layer to get the final prediction. This is a really simple case. They just use a linear layer and to get the final prediction, so that they can avoid some architecture, maybe architecture benefits on those features. So this is the most simple classifier. So this can directly show the effectiveness of the feature representation. And we can find the result. And these two graphs are maybe too messy. So I will highlight this line and this line. These two lines are about the clip, about the model using clip representation, and they got the really good performance. They output all the other features, and we can. They also just want to tell us, and maybe you are very confused about the forward pass GFLOPS per image. This is just show the, you can just regard this as the size of the model. With the size of the model increase, the average score will increase. This is how I interpret this picture. I saw a question. Does this image encoder from clip contains? Okay, I will first answer Chen Xiliu's question. Yeah, they also just we cannot prove the clip feature has linguistic information, because there is no specific way to test if a feature have linguistic context. Even for the word embedding, we can just know it has some linguistic feature, like we multiply those two vectors to get a similarity score, like we multiply dogs and cats and get a high score, and we multiply cat and a bat and get a low score. And this can imply this representation have some linguistic features. And we cannot use a specific way to show this it has some linguistic features, but they also use this model, and this quite like some their expectations to expect those features has some linguistic features, because they have to multiply with a real linguistic feature, and if they don't have the linguistic information, they cannot match, because the similarity score may be low. So this is my understanding. The Garbo Simmons just asked if the supervision is that noisy, why we should trust the 1 to 2 shot result at all. I think it shows something about yes. This is some tricky way in the field shot, because from my experience, I just found some paper can show good performance on 1 or 2 images. There is even a field called one-shot training to get those. So maybe this model can perform bad on 1 or 2 or 3 images. Doesn't mean those models, there's no model can perform good on 1 or 2 image. So for this model, maybe we don't have to trust the results from the 1 or 2 shot results. Yeah.
Yeah, I agree, I guess. The main, I think Barris highlighted an important difference for the 0 shot versus 1 to 2 shot comparison, which is that the 0 shot is using the prompt engineering and computing dot products between the text embedding and the image embedding, with the text embedding reflecting the prompt. But the 1 to 2 shot is using like a linear classifier layer instead. So I think the noise is like one possibility, right? But there is also the possibility that the difference in inference methodologies contributes to kind of the performance difference.
But the you can finish. Sorry, I just have some lag.
That's basically all I wanted to say.
Yes, the author also mentioned that the function of the image, the text encoder is just to generate some weights of a linear classifier. You can treat the feature from the text encoder as the parameters of the one linear classifier. So I think the experiment is quite equal, because we just use the at the end we just use the image feature to multiply some parameters to get the final result. In the original experiment setting, the image feature will just multiply with the text feature, and those text features can be regarded as a set of parameters. You can regard this as a linear classifier and to get the final result. And for the few shot settings, there are real defined linear classifier. So I think this experiment can be convincing. Yeah.
So in the few shot settings, are you updating the weights for the entire clip model? And I know probably this is in the paper, but it's a very long paper, and I don't
yeah, the author indeed mentioned something about this, because during training the text encoder is updated, so the weight of the text feature is updated by the whole training process.
Okay, thanks.
Okay, it's okay. Okay, let's continue where we were. Okay, the clip representation. Okay, the other experiment the author introduced is about natural distribution shift, and I found this one may be quite confusing when I was reading this paper, and I will explain this to you maybe in a very easy way. And we just met Overlord, and in this very comic style, we were trained by this Overlord image, and we can identify the other overlords or in this 3D model, and this maybe the other skin also 3D model, and we also can identify the overlord in this very abstract and cute way. We can know this is overlord, but for the model, this is really hard, because the authors just argue that if we train on some specific data set, the whole model will not learn the real feature we want them to learn. They just will learn the distribution of those images in that specific data set. So if we transfer this distribution, and we if we transfer this 3D overlord to this abstract cute overlord, and the model will mostly get lost, because it won't recognize this, because the model just know, oh, there's some spikes and many eyes, many legs, maybe 6 legs, and a real long claw, and it can learn, oh, this has 6 legs, many eyes, and many claws, 2 claws, 6 legs, and some features like this. But for this, oh, no spikes, 2 eyes, 6 legs, no claws, this is not an overlord. So this is called natural distribution shift, and this is why the authors wants to perform the experiment on this phenomenon, and we can show the result of the clip, and the image left here just showed if we sample the image from one class, like if we sample from we can see the image night here. We can, for the banana cases, maybe we just sample 5, 6. Maybe we just sample 2 images to train the model to show if the model's performance, to show the model's performance. And we sample 4 images, the model's performance in theory will increase. And maybe we use a whole data set, the model's performance will be the best. And this is the ideal line. They should be linear, because ideally, as we increase the training data, the performance will just increase linearly, because more data, more good performance, right? But the real case is not that. As for the comparison, the standard ImageNet, as we see, if we sample under 95% of one class, the performance will just as bad as 16%. And if we sample more than 95% of data, the model's performance will increase dramatically. So this indicates that the model can just learn the distribution of the whole class, and from all the images from one class. And if we just sample those images, the model won't learn anything, and they will get lost. And for the clip, they also show that this trend is more linearly than this standard ResNet, and this is the meaning of this figure. And for the second figure, they are more like, okay, x-axis. Okay, the x-axis is just about, let's say, from this case, I will just, sorry. Okay, I will redraw this. Oh, why I cannot erase them? Okay, I will just say that. Like we have, from here, for the ImageNet data set, we have 6 images, and we want to sample those images. Like if we have the banana class, we have 6 images, and we want to sample those images. Like we want to sample 50% of the images. So 6 image times 50% is 3 images. We use these 3 images to train the model and evaluate them on the whole distribution of the data, and the performance will be lower than if we train the model on 6 images, right? And this procedure, the X is just about this, how much images we sample from the whole class. For the banana class, it has 6 images. We can sample 25 is maybe 2 or 3, and 50% 3 images, and 80% 5 images. Okay, can this explain your question? Okay, great. Okay, let's see about the second part of these images. This is more like what I introduced you in this page. We can identify different style of overlords, and this one is just to let the model do the same thing, because in the original ImageNet, you can see those bananas are really bananas like we usually see in our daily life. But in ImageNet version 2, those bananas becomes to green bananas, and bananas on the tree, and peeled bananas, and bananas with some other fruits. So this distribution, this image distribution is different from the distribution of banana class in the ImageNet. So the model cannot, they also argues that the model can just learn the feature in the data set for those class, like how we human identify a banana. We identify its color is yellow, and it smells like banana. It's more like smells like fruit, and we also find it's a long object, And after we train on this, we know everything confers these features are bananas. But the model just know, oh, like the plain example I mentioned before. The plain example is that the plane has wings and bananas is yellow, and the model will train on this data will just know, oh, if something is yellow, it has high probability to be a banana, and it had a wing, it can have a high probability to be a plane. So the model cannot really learn what we want it to learn. So in this case, if the banana becomes green, it won't recognize this as a banana. And for the ImageNet, this one is just a comic style of banana, and I don't think the model can do this well. So they also just test many possible distributions of bananas. And for the ImageNet 1.1, ResNet 1.1, we can see as those bananas goes more abstract, and the whole model just gets some weird, because during the last row, you can see even our human cannot recognize those as banana easily. So the model just gave us a very bad performance, 2.7. It's quite bad. And for the clip, this clip can get almost 70% accuracy on every distribution. So they also can show that our model is good. They can transform from ImageNet dataset to the other ImageNet version 2 or ImageNet A dataset. Yeah, this is the logic of why the authors wants to do this experiment. Also, the authors want to compare the performance of model and human. So from this image, we can see the dataset is about, new questions. 0 robotic and natural distribution because they reference the text result. Yeah, I think so. I think this was also argued in their paper. Let's back to the human performance. The author compares the clip with human, and we can see this. They just perform this experiment on the Oxford PATH dataset. This dataset is just about a bunch of cats and dogs, and to let the human to recognize if this is some specific type of cat or this is some specific type of dogs. So from this result, we can see that quite surprisingly is zero shot clip is beat the human performance is quite crazy. But as I mentioned, this is one data set, and this data set is very objective, and the task is very easy. So there is possibility for those models to beat human, but this cannot prove that this model can have better performance like on other tasks than human. So they just show the model can outperform human on this specific one data set. Okay, let's go to the limitation of the model. As the author mentioned, for the limitations, the first one is the model is very huge. So we cannot easily to drag those models into the industrial fields. So it's quite hard for the small company to afford this model. And the second one is the model has really poor performance of abstract and system task, like the task we need to do some inference. Like if I give you an image, some which contains some numbers and letters, and I ask the model how many numbers in the image, the model cannot really understand what the number means at first, so it can go bad. And it cannot also recognize different models of cars like BMW, Toyota, or Honda. So the model can perform really bad on some tasks that need us to us human to make some inference. So this is also the common problem for all the machine learning models. And the third one is the author's comment is just like generalize poorly to data that is truly out of distribution. Like I trained this model on the 400 million data set. And if I give the model a picture of overlord, I don't think this model can know this one is an overlord. So the overlord picture maybe is the truly out of distribution picture. So the model cannot really know this is an overlord. And the last one is this model is not a truly generative model because we also, although we don't have to create one-hot vectors as labels for each image, we also need to create sentences like the multiple choice options for the models to choose. So this is not a truly generative model, like we just input an image and let the model to tell us what this image is. This model is just let the model to choose one correct sentence from the other three sentences. So this is not a really a truly generative model. Okay, let's come to the broader impacts. The broader impacts is the two common problems of all the pre-training model will face. The first one is bias. They also just use some human race data set and to let the model to classify some human images to some crime related categories and non-human categories. And the model will more likely to put white people to crime related categories and to put Indian to crime related categories. So this is the bias of the model. This model also remains some of the problems of the bias. And the second one is surveillance problem. Like this is, they also said this is a very strong model. So this model maybe can identify us, like give us some spots on our head or our body, and so that someone can use this as a surveillance technique. And they also just do some experiments on this, and the results also show that this is not a big problem for now, because they also performed experiment on some celebrity data set and found that the model performs poorly on recognizing celebrities. So the model doesn't have the ability to surveillance us for now. So this is a surveillance problem. And finally, we come to the discussion. The first question is about how do you think about a very large model? Are they really learning? The reason why I ask this question is about I heard my friend just gave me one point. It's just the model large as bird as clip. They need a lot of data. For this model, they need 400 million data. So if the model just remembered each data, or they learn some features of the data, like if we want the model to classify horses, we don't know if the model just remembered all the possibilities of horse and search them in its memory, or they really learn, oh, the horse is mostly black, white, brown, has very long neck and has 4 legs, had very, very good tails. We don't know if the model learned this, or the big model just searched for its memory, more like some abstract database to search, oh, this image I met before. I just searched this, oh, this one I met before, and this is a horse. I give you the prediction. So I just want to ask how you think about very large model, and are they really learning?
I think since the model performs well on 0 shots, so it may lead us to think that it is really learning, because it performs well on zero shots.
Yeah,
Would be correct?
that can be, yeah, that can be some this. I don't think this question has a correct answer, because the knowing if the model is learning is also a very hot research area in machine learning or deep learning. So yeah, the zero shot may be some sign of the model is learning, but it can be some sign of the model is not learning, because if we cannot know if the 400 million data just really has those concepts, like we don't know if the model was trained on all the bananas, all the possibility banana pictures, or all the angles of banana pictures to get the final results. So this one is just some very tricky problem. How close is this? Yes. I think this one is great. So this could be depend on how close the distribution of the zero shot data to the pre-training data. And the authors also performed some experiments of the data overlapping, and they found that the data overlapping between the pre-training data and the prediction data is really low. So this can be some evidence to show that model is really learning some high-level features instead of just searching all the possibility of each model. Yeah. And we can come to the second point. This just come to me maybe just 2 or 3 weeks ago. I just saw a good video about the next generation machine learning, and but this video is too long, so I won't play it here. And this video is a interview with Andrew Wu, and he is a really great AI and machine learning people. So he came up a really good idea of maybe the next era of machine learning is to transform from architecture-centric model to data-centric model, because during past 10 or 20 years, our research is mostly focusing on the architecture like CNNs, RNNs, transformers, BERT. We just dedicate to build a really complex and very big, deep models to let the model learn at many high-level features as possible. But he argues that during the past 10 or 20 years, we have explored many useful architectures, and the model still remains some problems like bias. And if we just put some noisy data or some biased data, because our human, the data just comes from our history. Our history has some bias on some races or some genders. So this data is written as a history, as text. So if the model receives those biased text or data, so the model can be biased. So he argues that maybe the next generation model can be, we can put our research on how to build data to let the model better learn something we really want them to learn. Like the banana and the plane example, we can build as many plane pictures as possible to show all the features of the plane, and not just the plane has a wing, or not just some yellow bananas. We can build some pictures had some green bananas, small bananas, and bananas on the tree, so that the model cannot cheat, cannot learn the bias. It turns out can be something we really want it to learn. So this is a fun point here. So I also want to put it here. And the last part is about the QA part. So if you have any questions, you can just communicate here, and I'll wait.
Okay, any questions?
Yeah, I have a question. Does this paper provide the math formula to abstract the model and also to find like optimal parameters, or say find the optimal structure to solve these solutions? Because in my understanding, this paper just show they give a structure, and then it has very good performance in the evaluation part, and it does better than others, and that's it. But it does not have a high level conceptual and to show us it is good.
Yeah, I think the first point is this model training procedure is really huge, and normal people cannot easily reproduce the whole experiment. And indeed, the authors didn't give us the code or the mathematical expressions. So maybe they are in the company. So this is some business secret, I think. I really come by a lot of papers just don't provide the concrete hyperparameters, learning rate, and even they don't give us code. And I will say GPT-3 is something like that. Yeah.
For this question, I think the model architecture, they provide us with information, right? They show you the architecture. I mean, for the images, we can use ResNet or we can use VIT, right, as an encoder. Then based on the representation, we can compute the cosine similarity matrix and then further feed it to the softmax. The other define loss function based on cross-entropy, if I remember correctly. I think based on the description,
yeah,
we should be able to reproduce this model out, right? Even though we cannot train it, but it should be easy to write the model out based on PyTorch, right?
Yeah, they also give us the main part of the code of the model. So their architecture is really simple. Yeah.
Okay, thank you.
Okay.
Yeah. So any more questions?
Yeah,
there's question. Okay.
Yeah,
okay, please.
Sorry. Yeah, I had a question. So basically, in the paper, the authors mentioned that the performance of their model is better than few short classifiers, but maybe not as good as 4 or 16 short classifier. So they say that you can do scaling to improve the model, and they also mentioned that it's good for a broader classification, but in fine-grained classification, like distinguishing between car models, it's not that good. So they suggest scaling the model. They say that maybe 1,000 times scaling can improve these shortcomings. So I just wanted to ask that is this kind of scaling even possible? They suggest 1,000 times scaling, but is this scaling even possible with the resources we have? I mean, they are already training on 400 million data points, and is the scaling even possible, which they are suggesting?
For my understanding, I don't know if this is correct, but I have some I thought these questions. For my understanding, is just this is a pre-training procedure. So maybe for those domain specific or some task need to recognize some specific car models, maybe we still need to use some fine-tuning method to let the model adapt to the domain. Yeah, I think this is why the authors want us to do some scaling here. Yeah, I don't know if professor have any suggestions on this.
I have no other comments.
Yeah, got it. I mean, I get that fact that for more specific tasks we can maybe train the model in that certain direction. But does that not defeat the purpose of generalization? Like I was confused by this also. In the start,
Yes.
the authors say that, like GPT-3, they want their model to be general, but then they suggest that, you can do specific training to improve on certain specific tasks.
Yes, I think this is we have to sacrifice the generalization, because if we really want the model to recognize different models of cars, maybe the model needs to be fine-tuned on the car data set, and it will definitely sacrifice some ability of generalizing to the other data sets.
Yeah, I get it. Thank you.
Mhm.
Yeah, I have a question about the prompt engineering part of the model, actually, but like it's not like only to you, but like for everyone. Like I guess like one of the main points that can be improved in this model is like how we like give the prompt, so how we generate the prompt for the class, because I mean this is actually one of the most essential parts in the testing, but like they use like simple prompts like a photo of something, or they also mentioned that they tried using an ensemble of some prompts, but like this is definitely like, if for example this prompt is not it's not the same distribution as for example the input text, which I guess isn't, then like we cannot expect to get good features out of like those like simple prompts that would lead to like correct classifications when we do the softmax over all of them. So like, do you think that like some improvements can be done there to generate like some prompts that are more like the prompts that are given in the training set, like that are more like the text descriptions in the data set for those images?
Okay. The question is that the authors mentioned a really simple prompt generating method, and the question is that are there any better way to generate those prompts to improve the whole performance? And the first one I want to say is that maybe the authors just tried some things and they reported the most simple or most effective ways. So training neural networks is just more based on experience, even if those experience is not quite corresponding to our daily common sense. So maybe a photo of something is not meaningful for our humans, because a photo of a bird or a bird has no difference. But for the deep learning model, maybe it just needs maybe it just needs the length of the whole sequence to be maybe 4 or 5 words, so that it could be generate really good representations, because transformers needs to put its attentions across the whole sequences. So I think using the first one, I think using the simple prompts may not be a bad idea. But if let me think of how to generate a good prompt, maybe we can use something more like we can enclose more context, not just a photo of something. We can use a sentence or some short descriptions to add the text of the image. So I think a distribution, the description can be a good context-rich representation, comparing to just a photo of something. Yeah.
I have a question too. So can we attribute the zero-shot performance of this clip solely due to the way we train it, solely due to the prompts that we train it on?
Sorry, can you repeat this?
Is the zero-shot performance of clip only due to the prompts that we train it on, like the sentences, for example, if we say, if we train the model, say, let's say, if it's a bottle on a chair, so so maybe the model learns both how a bottle looks and how a chair looks, and when we suddenly give it a chair, it recognizes a chair. Is it solely because of the prompts that it is good on zero-shot learning?
I don't think this is quite true, because I list the prompt engineering as a trick is just about this is not really the very necessary part for the training, because the author's idea is to use natural language as the label. So the label doesn't have to be the prompts, but the authors just found some images don't have, maybe I will just draw here, here's man, and this image's title is man, they are .jpg, okay, that's it, it's man.jpg, and this one is actually not a good prompt, so the authors just transformed into a photo of man. And this the number of the images just have one word is quite a small proportion to the whole training data set. So I just classify this as a trick, not the most important part to train this model, because most of the images just have some descriptions like BMW or a red BMW, yeah, .jpg, yeah.
All right, yeah, thanks.
I had an idea. It's not really a question, but an idea. So for Clip, Clip combines image data and NLP to make its predictions, right? That's how the model is built.
Yeah.
So I was thinking, could we combine data from other domains to build better models? Like MP3 files was one thing I could think of. So would increasing the number of data files you're using complicate the model or really help with the predictions? What do you think?
Yeah, I think this is a good research area, because the method we use here, the general method we use here is called multimodal representation. So it combines two data from two modalities. So sure, those two modalities don't have to be images, text, can be images, graphs, images, or like some other data structures. I think this can be possible. Yeah.
All right, thank you.
I have a quick question.
Okay.
I'm just curious the procedure of training for the clip. It looks like all input texts are almost the same except the last word. Like all input sentences, like there's a horse, there's a bird. Why we just put the sentence inside this model rather than the single word? Is that because the transformer requires a sequence of data, like a sentence?
Yes, like I mentioned before, the experience sometimes does, the model's experience sometimes doesn't correlate it to our daily common sense, because the transformer, if you notice, the transformer will draw like, okay, I will have a new page. The transformers will, most of transformers will draw like it will have many attention heads to the others. So the transformers can have good performance on some context-rich sentences, not just a word. So you need some context to finish this. At least maybe 3 gram or 2 bigram. Yeah, I don't think the one word is good for all NLP tasks. Yeah.
Yeah, that makes sense. And another question about the zero-shot clip. for the zero-shot clip, this model, we can extract the image feature representation from this model, right? And then we can transfer, this model, these frozen layers on other text, on other light to do other tasks, right? I'm just curious why. I'm just curious that how does the zero-shot clip to predict the unseen clause and compare to the ResNet ImageNet this data set?
Okay, this is just about how the authors did the zero-shot procedure, because the author mentioned in the paper is how to do the zero-shot clip. I will show you that exactly the slide. Wait for a minute. Oops, it's too long. Okay, this one is how the authors did the zero shot. They just use in our case, our data set just has 4 classes. So the authors just search through all of the 4 classes and substitute the class's name into one prompt. So it could be become a pairing problem, so that the author can so that the model can make predictions. And for the zero shot, I think it's just this is also the question I asked for the really big model. We don't really know if the model really just like this. The model trained on some data set and test on the other data set doesn't mean those data sets has no overlapping concepts. Like they also just test, oh, this banana image does not exist in this data set, but they do not ensure that this data set doesn't have different banana images. So maybe it's just a model know the feature of the bananas so that it can recognize the different banana images in the other data set. Yeah.
That makes sense. Thank you.
Mm-hmm. Oh, I also noticed some questions in the chat. I will look through. Oh, that's a very long chat. Okay, that was from the last question. The diagonal matrix. This one just use some concepts called contrastive learning. What is contrastive learning? In this, I showed here. Give me a minute. I will just go to this one. Can you see this? In this slides, I offer you four sentences, and those 4 sentences are so this one is called the positive label, and those 3 are called the negative label. So it is using this way to let the model to separate apart all the representations. So our human can say this is quite robotic, not natural, but this is necessary for the models to learn how to distinguish the dog image and dog sentence with the other different representations. Yeah, that's how it does. So there's an area called contrastive learning. Just use the similar idea to pull apart the different images and text.
Okay, so probably that's it for today, because the time is pretty much up. If you have any more questions, probably we can discuss via Discord instead, because we have one Discord group. If you have any question, you can propose online, and then the presenter can help you answer the question by replying you instead. Okay, so this paper is very good. And if you have any new ideas, you can use this paper as a foundation to propose some new problems or new methods for your projects as well. In the next week, we will have 2 other presentations on both Alpha code as well as one paper on self-driving car by fusing images and point clouds. And so please read these 2 papers as well before class, and then we can have a talk in the next week. Okay, so that's it for today. And let's thank the speaker.
Okay, thank you very much. Thank you very much. Thank you for all listening.
Okay, so that's it. Thanks.